Right, yep, I'll make a start then. So yes, yeah, thank you for having me. So yeah, my name is Saachin Bhatt. I've just finished my undergraduate degree in digital and technology solutions at the University of East London, and the research topic that I'll be presenting today is titled Machine Learning Based Cryptocurrency Price Prediction Using Historical Data and Social Media Sentiment. And just before I continue, I just wanted to say thank you to Dr. Mustansar and Dr. Mohammad for their very valuable contributions towards this research. So the overview of what this presentation will contain. So we'll first start with the introduction. So that's just a background about the use case and the problem we were trying to solve. We have the literature review and gap analysis. So trying to understand what previous work has been done, as well as the methodology as well. So how I went about implementing what algorithms I used. Then after that, we'll have a look at the data sets I used. So there are a few data sets that I pulled together for this research. After we'll have a look at the experiments. And these are, again, what algorithms were used, kind of assumptions that were made as well throughout the process. Then we'll kind of finish off with the results, conclusion, and future development for this work. So as the introduction, so the current issues for traders at the moment is that the cryptocurrency market is extremely volatile, probably more so than other stocks such as commodities or index funds. And you know, if you follow kind of crypto or the news, you would have heard that, you know, small news announcements or a build-up of excitement on social media, and it seems to be Twitter specifically, can essentially make the crypto market price either skyrocket or crash within a very short amount of time. And as a result, for a trader, it is very difficult to keep up with monitoring and analyzing all of these sources and understanding how it would affect the market price. So there are two main goals of the study that we set out to achieve. The first one being to provide an insight to investors as to whether tomorrow's Bitcoin closing market price would go up or down relative to today's. And the second one being to understand whether the use of Twitter sentiment would increase the performance of prediction models. So is it actually valuable to be analyzing and looking at this Twitter data or not? So just a brief overview of the literature review. So the first theme that we saw from historical work is that using tree-based algorithms for trend classification. So that's like the actual predictions of whether the closing price is higher or lower than today's closing price. And it seems that these tree-based algorithms were highly effective when it came and, you know, were proven efficient in analyzing these kind of multi-dimensional and complex relationships. And, you know, these are some algorithms that I actually implemented, and we will see kind of further on in my methodology. So the second one being using the volume of tweets for market predictions. So, you know, the sheer volume of tweets has been proven to be a very reliable indicator of sentiment and by extension, you know, kind of the market movements. And historical studies have shown that increased Twitter activity, specifically surrounding a particular cryptocurrency, correlates significantly with its price fluctuations. So, you know, harnessing this insight in our research was pretty crucial, as it was highlighted quite strongly within our research. The third point being that the time lag analysis for the optimal performance in the crypto kind of market prediction is 1 day or 3 days. So we've seen analysis of both, and in the research that I did, I went with the 1 day and stuck with that assumption. And then the last trend that we saw was there was a high accuracy achieved using LSTMs on higher timeframes. So the timeframes I'll explain next. Oh, gosh, sorry. Yeah, the time frame that we used in the research was daily, and due to the temporal nature of our data set, LSTMs you know, seem to be highly effective as well, alongside, you know, using it with time series data. So now I'm moving to the actual gap analysis for our literature review. So the first point being that, obviously this is a general lack of research on the actual effectiveness of using Twitter sentiment as a predictor itself. The second being that there are quite a few similarities in approach of the data and models used for the actual sentiment analysis of these tweets. And we saw that Vader sentiment analysis and using text blob as well. So these are libraries and techniques which are available. Those two are quite common sentiment analysis techniques. So then the third point being that there's a limited interdisciplinary approach. So many studies at the moment focus either solely on using sentiment analysis of tweets and market data, or just on analysis of on-chain data, which is blockchain data. And obviously blockchain is the kind of the underlying infrastructure for how Bitcoin is run. So the potential of integrating both sources together is something that hasn't been explored, and it could, potentially become more robust, which is something that we've explored, in our research. The fourth point being the sentiment analysis complexity. So obviously we are using Twitter data, which is quite informal. So there are obviously a few nuances when it comes to this sentiment analysis, including irony, sarcasm, and specific slang or colloquialism that's used on Twitter, and these are quite hard to capture through the use of some of these sentiment analysis techniques which have been previously used. So we want to see how we can leverage those and pick up on these type of things. So the following diagram shows the actual project methodology and implementation approach that we took. So you can see there's kind of two streams of data, one on the left, which being the actual Twitter data, and on the right being the Bitcoin market data. So starting from the Twitter data, so we got data from 2014 to 2020, or specifically around Bitcoin. And as you can imagine, there were quite a few kind of emojis, hashtags, things like that. There's a lot of cleaning that needs to be done. So we took it through a pre-processing and cleaning step. And then once we'd done that, we then calculated sentiment for each day. So yeah, we kind of aggregated all the tweets up daily and calculated an average overall sentiment for the tweets for each day. And to calculate the sentiments, we implemented two key methodologies, one being Vader sentiment, as kind of mentioned in the literature review, and the second being a Twitter Roberta, which is a fine-tuned BERT model or Roberta model, specifically for Twitter data, to explore how the performance also changes using this. So then that was our kind of Twitter data set, collected and built. And then the other stream of data being the Bitcoin market data. So this is kind of your open price, closing price, highs, lows, and volumes. So we went through an exploratory data analysis and pre-processing step to make sure everything was ready for our modeling. We then combined this with the Twitter data set and introduced a lag factor, which is similar to what was mentioned in the literature review. We used a 1-day lag for this research. So once we had this combined data set, we obviously labeled it daily. That label was 1 or 0. So we built a binary classification model to understand whether tomorrow's closing price was higher or lower than today's closing price. And if it was, then we'll label it a 1. If not, then we would label it a 0. So now we have this data set for classification. We then ran it through 6 different models and applied hyperparameter tuning on top. So you can see from the diagram, we ran it through naive Bayes, k-nearest neighbors, SVM, logistic regression, XGBoost, and then a multimodal model as well. And then we ran this experiment with the Twitter data and without the Twitter data. So using the same algorithms for our experiment to fairly understand whether using and including this Twitter sentiment data improves the performance or not. And then at the end, we then obviously evaluated, like for like here to help come to our conclusion. So here's a quick snapshot of the kind of Twitter data set. So you can see the cleaning process for tweets. The original tweet contained a few characters, whether it's the exclamation mark or the $sign as well. So you can see the process in which we took to break it down through removing punctuation and then tokenizing it. So splitting it by each word and putting it into a list, removing these stop words such as the, a, it, things like that. Stemming, so only keeping the key part of the word, and then lemmatizing it afterwards. And then you can see the data transformation process is kind of what I just explained. But in other examples, we would have mentions, so at if you want to tag someone, or we would have URLs as well, which people are referencing, but we didn't include that for this. So that's the Twitter the process, the cleaning process. So then once we had this, we then looked to calculate the sentiment for each. So you can see the lemmatized tweets on the right, and you can see the sentiment alongside with it. So yeah, you can see this has been done daily, and it's been averaged up. So obviously you have multiple tweets on a single day, so calculate the sentiment for each and then aggregate this up for each day. So our second data set was the actual Bitcoin market data. So you can see, as I explained, the raw data had kind of your volume, high, low, open, close. And as you can see, the values for volume are extremely high, almost on a different scale compared to the other values. So what we had to do was we normalized all the values in our data set. So they obviously they're still relative size to each other, but the volume wouldn't have an unfair weighting once we process it through the model. So everything had equal weighting going into the models. And then we have the table describes each attribute. So the volume is obviously the number of shares that were traded at that point in time. The high is being the highest price at which the stock was traded, low being the lowest price where the stock was traded. Open is the price at which the stock began trading at the start of the period. So the period that we were using for this research is the day. And the closing price is the price at which the stock ended or closed at the end of the day, or when the market closed. So here we have the on-chain data. So this is the blockchain data that runs essentially behind, or the kind of underlying infrastructure for how Bitcoin is run on. So you can see that we have got five columns here, and essentially we have your kind of volume. So this is almost similar to what we saw in the last data set. This is the total transactions volume in a day. The TX count is the total transactions executed in the day. Average difficulty is the computational complexity to mine the new block for the blockchain. Generated coins, number of coins mined, and the payment count is the unique payments executed within the blockchain network during that day. So this is a data set which we haven't seen, or hardly seen, in historical research that we also look to include. So we did a similar process. You can see obviously each column, the actual values are almost on a different scale. So we again did the normalization process for this also. So then what we did, we obviously wanted to create one big and one full data set with the market data, the blockchain data, and obviously the Twitter data. So here's obviously a snapshot. You can see everything's been normalized. It's on a daily time scale, and we have all of our various attributes. And then obviously what we did was labeled it and lagged each feature by a day, which is an assumption that we've made for the point of this research. So when it came to modeling, as you saw in the diagram, these are the 6 algorithms that I had used, as well as the sentiment. And once these algorithms were developed, we then went on to do hyperparameter tuning, which we did across using grid search, a randomized search, and Bayes search as well, which is obviously a Bayesian approach. And again, the modeling assumption here is that the tweets affected the market after 1 day, hence the 1 day lag. So this is just a little background about how the Veda sentiment works. So you can see it's a lexicon, or it's more of a rule-based sentiment tool, and it's been known to do well in calculating sentiment for social media content. Hence why we used it for Twitter, and it's also really good at understanding the context for short informal text, which for those on Twitter, you would see a lot of, that. So in the first table, you can see that each word has a sentiment rating. So again, this is a rule-based approach. So we almost have a lexicon or dictionary of words and their sentiment. And then when it comes to seeing these words within a sentence, the overall sentiment is then calculated. It's almost like a mapping table and then doing an average. So you can see those 5 words, their individual sentiment rating, and then kind of we include all of them into a sentence. You would see that we have a what the positive sentiment value is, the negative and neutral sentiment values are, and then obviously your compound, which is your overall sentiment. So the overall is a positive sentiment. So then once we obviously modeled the Veda sentiment, we moved on to actually exploring this Twitter Roberta, which is quite new. It's only been fine-tuned very, very recently. So we wanted to include this, and this is a lot better at understanding kind of the irony and those small nuances when it comes to actually using Twitter data, because the underlying infrastructure or technique method for this is that it uses a transformer model. So when it comes to kind of the encoding and things, it's much better to understand these emojis, abbreviations, hashtags, a lot of what you'd see in tweets itself in this rawest form. So this is a small diagram to explain kind of how it works. You initially start with the tweets, you then pre-process it, and then you actually put it through this Bhatt model. So you add a token, you encode it, so you send it into, or you transform the given text into a vector and put it into a vector space, which captures context, and then you feed it through the model, and then out comes your sentiment. Then the last technique that we used was a kind of multimodal fusion model. So essentially what we did is we initialized like 3 separate branches. So we set up this model, we created 3 branches, one for sentiment analysis, one for blockchain data, and one for the Bitcoin market data. And the process that we went through was we processed the sentiment data independently using a dense layer in the sentiment analysis branch. So the output of that would be the high-level features that captured the sentiment dynamics in the Twitter data. The second part being processing that on-chain or the blockchain data independently, and that was using an LSTM layer. The second process being processing that blockchain or on-chain data independently using that LSTM layer in the on-chain attributes branch. So the output of that would be sequence-based features that reflect the actual long-term trends on the actual on-chain attributes. So you can see each of these outputs are capturing the dynamics or the actual trends here to kind of bring it all together. And the last stage being processing the Bitcoin market data using a suitable layer. So here we used the LSTM layer, similar to what we did with the blockchain data. And again, the output was more features that reflect the dynamics of the actual market trends. So you can see now we've captured the dynamics for the core 3 data sets. So then bringing it all together, we have the model kind of integration. So we concatenate the outputs from all of these branches, integrate the high-level sentiment features and the sequence-based on-chain features and market data, pass this through another dense layer for further feature extraction, and then run it through a final sigmoid activation layer to produce a binary prediction, which is like similar to what you would use on a logistic regression. The last step being the feature selection and the optimization. So we performed feature selection that determined the relative importance for each modality, compared the model performances with and without specific modalities, and then conducted hyperparameter tuning to optimize the models and get those optimal parameters as well, and ensure the appropriate complexity. And then again, the model finally outputs the prediction or the classification as to whether tomorrow's closing price is higher or lower than today's closing price. So here is the results. So using that last approach I was just discussing, produced the best, alongside using the Twitter Roberta for sentiment analysis, actually produced the best result with an F1 score of 0.85. So the diagram shows you for each model what the results were using either Vadar sentiment, Roberta sentiment, and the baseline is without using sentiment. So you can see in the majority of the occasions, the model performance is much higher than the baseline, which supports our initial hypothesis around Twitter. It is beneficial to now use Twitter in this analysis. And from that, actually using a fine-tuned model, with the framework of the multimodal that I just explained, actually produces the best results. And you can see the optimal parameters on the right, which were gained from the hyperparameter tuning. So to conclude, there were kind of three main further improvements for future iterations. So the first one being experiment with optimal lag time. So from our literature review, we obviously saw that there was a promising work around using 1 day and 3 day, but experimenting with this more would be very beneficial. The second one being include more market and off-market features. So we have your RSI, your MACD, so your relative strength indicator, your moving average, convergence, divergence. So these are all kind of trading signals that are used. So including some of these could make for an even more powerful model. And the last one being weighting tweets' impact on the stock price movement. So one of the assumptions for this research was that each tweet has an equal weighting, but for those who kind of know and follow, if Elon Musk, for example, posts something on Twitter, compared to if I post something on Twitter about Bitcoin, the market would move according to his tweets and not mine. So including that weighting would be more, could add that extra layer within the model. But yeah, that's the presentation. I hope you all enjoyed it, and yeah, please let me know if you have any questions.